Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are studying the subject principles of compiler design, where we are having the 5 phases of compilation: the lexical analysis, index analysis, then the intermediate code generation, code optimization, and finally it is code generation. So, here we are having the code generation phase. The need for this phase is, that is how we are transforming the intermediate language into its equivalent object code. So, every compiler has to produce some languages, that is object program, and the important thing is the object program being produced by the compiler should be understandable to the machine. The machine, we may talk about the that is the actual processor, or it can be something like your virtual machine. So, whatever be the target machine we are talking about, your program should be understandable to that. See, for example, in the case of C++ compiler or C compiler, we will be producing the code for the native machine, and in Java case we will produce the code called bytecode, which will be produced for the virtual machine, understandable to the virtual machine. And there are cases where even have the high level languages in output, but provided that high level language is once again being translated by using maybe another compiler or a different one, so that the program will be executable at some stage, maybe in the current machine or in a different machine. So, we need to definitely produce the object program for the given high level language, but not directly. We will transform the high level language program into the intermediate language, and there are different formats of intermediate languages like the 3 address code or the syntax tree or triplets, like that, and from that we will transform it into the object program. So, now the question is, what are the difficulties and the challenges we are having as far as the translation of that is our intermediate language into its equivalent object program. So, those things we are going to study as far as this episode is that is concerned. Another important thing that we ought to recall here is, this phase is going to be a machine dependent phase. We have studied the lexical analysis, then syntax analysis. So, they are completely machine independent phases. The lexical analyzer or even the syntax analyzer has nothing to do with the machine. It is all working based on the language specification given in terms of the grammar for the language or the regular expressions for describing the tokens. But when you talk about the code generation phase, the code is actually going to be generated for the machine, so that we will be able to have the execution of the that is code in the machine, and we can see the output of the machine program on that particular machine. So, if you do not have any information about the actual machine where for which we are going for generating the code, then there will be lot of disparities in making use of the resources available in the machine, especially the registers, the memory size, the word length, and all. So, these are all the things that we have to understand. So, any code generator should first of all read the machine structure or the machine information, so that we will be able to produce the object code in an efficient manner. Let us see the issues first of all we are facing. What will be given for the code generator is going to be the intermediate language, and the intermediate language will be given as the input. The code generator is going for producing the object code. The object code can be produced provided there is no error in the intermediate language. That is very important. So, no code generator will proceed if there is going to be an error available in your program. So, now we look at the semantic analysis. All these are actually completed as far as the intermediate language is concerned. So, the code generator actually it is preferring the operands from the registers, that is a normal scenario. There are two cases, the operands may be available either in memory or in registers. If they are available in the memory, then it takes more time for fetching those from the memory for that is computation. But whereas in the case of these operands, if they are available in the registers, so they will be taking lesser time for the that is execution time, because even if you find that the that is the instruction size is also going to be less, provided the operands are available in the registers. And even we are trying to keep the computed results in registers as long as it is possible, because a value which you have computed most probably may be needed in the near future, and if you move it to the memory, immediately we will be forced to read it from the memory and put it on a register. For that we need to find out where is the register available, etc. So, we will try to keep the values in the registers once computed to the maximum extent of possible time, so that if there is a need for referring that particular value, then it will be referred from the register rather than moving it from the memory to the register. So, first we shall see that is what is going to be the types of object programs. There are 4 cases we are having. So, one is going to be the absolute machine language program. It means that these machine language programs can be placed only in fixed locations and they will be executed immediately. So, in the Windows and all we find that the COM files are there, .com files. So, they are the programs generated with the absolute machine code. So, there are advantages and even disadvantages for this kind of machine language programs. The advantage we can talk is like it is much simpler to produce object codes which are absolute, because we will fix all the address values, whether where program starts and what is going to be the control branches and the memory address, data address, everything is fixed. So, the code generation will be much easier, but the problem is whatever be the number of times we are executing that code, irrespective of time and that is date, whatever it is, we need the same memory for the execution of the program, which we can't guarantee that always it will be there, but it will be there provided there is no other program written in this way which requires the same memory for its execution. That is the issue with the absolute program. Otherwise, they are much simpler in terms of the code generation component is concerned. The second one is going to be relocatable machine language program, and it is allowing the program to be compiled that is separately, that is we can generate different modules and they all can be linked at dynamic time, that is together by the loader when there is a need for that. Otherwise, we can keep those particular object codes in the that is secondary memory itself, and any compiled module can be called from the object program, provided they are already compiled, that is pre-compiled, that is modules. And this very important advantage of these relocatable machine language programs is on it is not required that they should be reserved with a specific memory for the execution. So, we can go for that is any free memory, you just load it onto the particular free memory available, and then we will be having the code with the relocatable, that is locations. So, normally we will put it into some that is relative address rather than the absolute address. In the case of absolute program, we will be having the absolute address, but whereas here we will be having relative address. So, all these addresses will be added with some basic, that is starting location, so that these addresses are going to have there is actual address, but only during the execution time, but not during the compilation time. So, that is what we say it is going to be possible for dynamic linking and loading, and moreover it is not needed to load the entire program directly into your random access memory. Wherever it is needed, we can load it, and if not needed, we can unload it, so that the memory can be reused for the modules which are live at a particular point of time of that is execution. And the third one is going to be the assembly language program, which is much simpler in terms of generation when you are comparing with generating the object code, which is machine code. But once again we should understand here that if we go for assembly language, there is a need for an assembler which is meant for that particular language, assembly language, which will be producing the object code for a specific machine, so that this program execution can be seen, but not just the assembly. we can't see the output. So, an assembler is to be available, so that the program can be that is executed. And final one is going to be another high level language program. It is much easier, we are transforming one version of a language to another version of a language, or one high level language to another high level language, but provided that we want to have another translator that will produce the object code from the output language of this particular compiler. So, that is what the need for your that is high level language program as a target language. So, here is one example. Altron is a language for which is meant for algebraic transformation manipulation, and this is going to be a compiler that produces a Fortran program as output, and we know that the Fortran is having the compiler, and that particular program will be compiled by your Fortran compiler. The easiness is the advantage here is it will be much easier to design a translator that transforms one high level language program into another high level language program, rather than following the various phases like intermediate code generation, then object code optimization, etc., etc. So, that is what people will be trying to write compiler for a translator for a language to produce another language for which a familiar compiler is already existing. So, now look into the various issues available in the code generation. The first one is, so what is going to be the instruction to be executed? We may have there is a plenty of instructions available for us to generate the object code, but certain instructions will be that is creating, that is one particular, more than one instruction may be fit into a particular situation. So, now how do you find out the optimal instruction, so that we will be able to produce the object code which will run in that is less amount of resources and lesser amount of small amount of time. So, here is one situation. We have an instruction called add 1 to storage, and that is going to be increment operation. A variable called a is there, and that is supposed to be incremented. So, the operation is a is equal to a plus 1, and now there are two cases. So, this could be executed by load a, add immediate 1 and store it back onto a. So, there are 3 assembly instructions generated here, but suppose if you are having an instruction called AOS, which is called add 1 to storage, which is an implementation of increment operation. Now, you say that what is the memory location which is supposed to be incremented? AOS A, that is all. But rather than writing load A, add immediate 1 and store A, it is enough to write there is AOS A, that will automatically increment the particular location by 1. So, instead of writing 3 instructions, we write only 1 instruction. So, we need to decide on what is going to be the instruction to be generated for a particular context, that is the first problem. And the second one is, what is the order in which we need to perform the risk computations. So, the order is going to have some impact in the number of register utilization. So, or the number of that is instruction to be generated or executed. So, if you are performing a particular operation in some order, we may that is notice that the availability of registers or the availability of values in registers, these are the things, register availability and availability of values in registers. So, some value if it is available in the register, and that can be very useful for the that is next computation, but if you go for a different order, sometimes there is a chance that the values which are there in the registers would have been moved into the memory, and maybe for the current computation we need to go for picking up the value from the memory and putting it in the register back. So, it will be that is going for the optimal order or the right order will reduce the number of that is memory operations or memory fetch operations required for doing a particular computation. So, we need to find out what is going to be the exact ordering in which the instructions are to be generated, so that the computation can be done much faster. This is another issue. And the third one is going to be what are the registers available on the machine. So, because registers are mostly that is coming with the specific purpose and even general purpose also, and if there are registers which are general purpose, okay, no problem, but if there are registers which are coming with specific purposes, especially like the stack pointer, the program counter, these are the registers, but they are capable of doing certain operations much faster. Like if you are handling a stack, the stack pointer will be much useful for us, and if you are just counting the instructions, next instruction to be executed, then program counter will be much useful. So, there is a need for using these kind of registers especially for the specific purposes, this one. And another thing is like sometimes machines will be having register pairs. So, we in 8086 and microprocessor we see that AB pair, DE pair, CD pair and DE pair. So, these pairs when we combine them, we will be able to handle larger data values, like rather than 8-bit data we can even handle 16-bit data, or rather than 16-bit data we can handle even 32-bit data. So, instead of that is doing the computation by parts, if you have a mechanism for computing them in a single instance or by using a single instruction, that will be always advantageous and it will take very less amount of time for producing the results. So, you try to find out what is going to be the pairs which are supposed to be combined for particular instruction case, and if you combine them we will be able to produce the computations much faster. So, these are the three issues normally we have to address when you go for the code generation. So, the order in which the things are to be carried out, and what is going to be the register being used, and what is the instruction exactly to be selected. These are the issues. I will continue this episode after a short break. Welcome back. So, we are seeing the various issues faced during the code generation component, and the next one is I talked about the utilization of the registers. So, if you are having some value in the register, we are trying to keep the value in the register as much of time as possible, so that if there is a need for referring that particular value in the near future, then definitely the value would have been picked from the register rather than going to the memory and moving it to the register and finding pre-register, etc., etc. So, what is the need for keeping a value in the register is identifying the next use for a particular variable. So, if you are so sure that a particular variable has no next use, or it is not necessarily to be kept as live from a particular point of time, then there is no point in keeping register that will be unwantedly that is occupying a resource that is most valuable resource as far as the computers are concerned. So, how do we find out the next use information? We will call it as the live information. So, there is a need for computing the live information. So, especially like if you are having an instruction of this format like A is equal to B of C, we can generate that is the instruction called add Ri comma Rj, but leaving the result A in register Ri, and this code is possible only if Ri is already having that is B and Rj has C, then B is not going to be live after this particular computation, because why we are having that constraint is we write the value back onto register called Ri, and earlier we had Ri with that is B, but after the computation Ri is no more pointing to B, or it is, and it is going to have the value called A. But at the same time we can generate another instruction called add C comma Ri if C is a memory location and B is not live, that is after this computation. So, in general to generate the code it is required to find out the information that are live after this the computation. If you find that certain things are not live, then we can go for reusing the registers, so that the code size will be lesser. The next use is see, for example, we are having a quadruple, or quadruple means an instruction with 4 components, that is the ith quadruple is assigning a value that is for A, and A is going to be an operand in the quadruple called J, that is it is going to be definition for A, and it is going to be the use for A. The definition happens in the instruction called ith instruction, and the use happens in the instruction called jth instruction, and there is a path from I to j without any intermediate assignment. So, we are able to reach jth instruction from the ith instruction, but in between them there may be some instructions available, but there is no question of modifying the value of A in between that is I and j. So, now we say that the definition for A in ith instruction is going to reach the place called j. It means the quadruple j uses the value of A computed at a point called I. So, now to determine the next use information, normally what do you do is we will make a backward scan from the end of the block to the beginning of the block and recording the next use, because from a particular instruction called ith instruction we can't determine exactly whether the particular operand is going to have a next use in the later stage. But if we start from the end of the block to the beginning, so what do we see first is the usage of the variable, but not definition, because definition precedes usage. So, when you start from bottom to top, we will find out usages. So, we will record the usage of the variables and their corresponding quadruple number or triple number into the symbol table. So, that we will be able to know that a particular variable's definition, what are all the places it is used, whether it is really used or not, all these can be collected. And now, if you are translating the program from the beginning of the code to the end, that is when the code generation cannot be done from bottom to top, but code generation has to be done only from top to bottom, but whereas the next use information can be computed by proceeding from bottom to top. So, you just record the information in the symbol table, and during the code generation we will be knowing whether a variable is having a next use or not, and if it is having a next use, how far it is, all these can be it is obtained, and you can decide whether it can be kept in the register for a long, or it is not required to keep in the register and the register can be reused or not. So, everything can be decided by looking at the next use information. So, there is another component called register descriptor that will be telling about what is there in a register. So, after computing next use information, we will be normally doing a forward pass throughout the block to generate the object code, and there is a need for thinking about register allocation. So, we will maintain a register descriptor that will be telling about what is currently in a register. So, if you find that there is a need for a read operation, and if the value is already there in a register, there is no need of going for additional read operation, because the variable is already there in the register. How do you know that? We know that by referring the register descriptor for each register. We will be initially making the register descriptors as empty, and whenever you move some value to a register, automatically the register descriptor will be updated saying that this particular register is having this value. So, with this available information, we can think about how we go for the code generation algorithm. So, it is making use of a function called get register function, and the instruction to be translated is A is equal to B of C. And now assume that this there is get register function is giving you the register required for doing the computation. So, most probably the get register function will give you a register for doing the computation, but if there is no register available and something like if an operation requires certainly register. So, if there is no register available, it will return a memory as the place where the computation is to be carried out, and sometimes we will find that this particular operation requires exactly a register. For example, like if it is going to be an indexing operation, something like that, a register is mandatory. So, in that case we will go for that is moving the already occupied registers value into the memory and returning the occupied registers as available registers. So, that is what the job of your get register function, which is described later. And now assume that we have L where the computation B of C is to be carried out. It can be either a register or even it can be a memory location also. So, now we are talking about where this B is available. There is a first operand. So, it may be available in the register or even it can be available in the memory also. So, how do you decide where the value of a variable is available? So, to find out what is in a register, we will consult the register descriptor. To know where a memory value is available, it is we will be that is talking about the address descriptor. So, you just consult the address descriptor of B to determine where is B. So, if B is already in a register, prefer that. If B is not in register, but only in there is a memory, then we go for moving that into a register. If B is already both in memory and register, prefer the value which is there in the register. So, if the value B is not already in register, then if it is not in L, that is L is the place where the computation is to be carried out, then we will move that B into that L by generating an instruction called move B dash comma L to place a copy of B in L. So, what this B dash is? The B dash is the address descriptor for B, which will refer either a memory location or may refer to the register based on the availability of B where it is. So, having done that, we will go for generating the that is instruction for doing the actual computation, which is nothing but op that is C dash followed by L, where C dash is going to be the current location of C. Once again it can be either a memory location or it can be even be a register based on the availability of the value already. So, now the computation has been done. So, we have to go for updating the address descriptor of A, saying that A is now available in L. We have computed A is equal to B of C, A has been computed, A is now in L. So, we are updating the address descriptor. So, the need for updating the address descriptor is when there is a need for referring where is A available, you just go and see the address descriptor, it will tell you that it is available in the register called location called L. So, L may be a register. So, if L is a register, then update its register descriptor to say that it is L contains A. And if the current values of B and or C have no next usage, then we can keep them as not live. A may have a next use because A is just computed, but there is no need that B and C should have next use. So, if B and C have no next use, then we can keep them as not live, and so that if they are already in registers, so those registers will be made available for reuse, and the appropriate register descriptor and address descriptor will be that is updated, so that B and C not necessarily be on your that is registers. So, if they have live next use, we prefer them always in registers, provided the registers are not mandatory for the next operation in that case. And now we can think about the get register function. So, here have the operation is A is equal to B of C. So, if B is in a register, we are returning that, provided it is not having next use, and if not, we will find out an empty register to do the operation. And if not, if you find that that is having next use, in that case we will try to that is move the value, or the situation is we need certainly a register for doing this operation. In that case we will go for finding an occupied register, we will move to the memory and then we will return that register. So, if these three steps are not satisfied, then we will return automatically a memory location as the answer where the operations will be carried out. So, when you are returning memory location for doing this operation, automatically the cost of the insertion will be there is more. We can say that the memory address means it requires 2 bytes or even more for representing the address, but registers, since they are very lesser in count, it requires less amount of space for describing the register number, which register we are going to use. So, we shall see one simple example where we are having an expression to be translated, W is equal to A minus B plus A minus C plus A minus C. The 3 address statement generated here is T is equal to A minus B, and U, it is another temporary variable, it is A minus C. Another temporary variable V is equal to T plus U, and finally W is V plus U. So, the code is generated as this way. So, first we move that is A to R naught, and we are subtracting that is B from R naught. So, look at the register descriptor, initially it is empty, now we say that R naught is having the value called T. The next is U is computed, we move that is A to R1, a free register, we subtract C from R1, and now we are having R1 contains U, that is the register descriptor, and correspondingly address descriptor can also be updated, that is U is in R1, that is address descriptor for that. Next computation is T plus U, we find that R1 is containing that is U, and another one is R naught contains T. So, both we are adding, and you find what is not needed further. So, T is not needed. So, we can go for updating R naught. R naught can be reused now. So, R naught contains V now, and R1 contains that is U, and the final computation is W is equal to V plus U, where we will be adding R1 and R naught to produce R naught as the result, leaving that R naught contains W and R1 is not having any next use. So, this is how we will be generating code for intermediate language. There is a block of intermediate that is instructions. So, update automatically the register descriptor and address descriptors are being used for producing the optimal code after understanding the live information and all. So, this is how we are generating the code generated, there is codes. So, to summarize that, first we should find out what is the algorithm to be used, and we need to know that is what are going to be the information to be collected from the machine, and after collecting the information we can address all these issues and we can generate code which is specific for the machine. So, the question component here we may have what are the issues in code generation, especially with the machine, because we are concerned about machine, and what is going to be the algorithm used for the code generation. And another important thing is that is how the next use information, because next use information are very important when you go for the optimal usage of registers and memory values. So, you are how you are computing the next use information, that is another possible questions. So, with this I complete this particular episode. Thank you all.